My son was interested from the previous project I did with the flying helicopter on how you would actually light some LEDs, so I thought I'd make a video about just LEDs. So you can see here that the LED with its two leads, one is longer than the other, the shorter one being the negative lead. The other way you can tell is that side here has a short flat bit on the side, and that's the negative end. So next thing we want to try and do is to try and light an LED. So if I take this 1.5 volt battery and put the longer positive lead on the top, we can see that the LED isn't going to light. So if we increase the voltage, we can take this 3 volt battery and put the positive lead on the top, and we can see that the LED lights. And now if we take this 9 volt battery and apply the positive lead here, we see that the LED lit for a little bit and then went out. And if we put it back onto the 3 volt battery, we can see the LED is no longer working. So you have to work out what the correct voltage is and current to put through the LED. In this circuit here we have the voltage, and the voltage is how hard the current is being pushed through the circuit, and the current's just the flow of electrons going through this circuit, lighting up the LED. We saw that when we used a 1.5 volt battery to connect the LED, it didn't have enough push to light the LED. We saw when we used a 3 volt battery that had enough push to light the LED, and then we saw with a 9 volt battery it had too much push and blew the LED. So here we have a multimeter, we have it set to the voltage range, and we can measure the voltage of something like a battery by putting it across the two terminals of the battery. So here we have a battery that's reading 7.88 volts. So this is a 9 volt battery and it's not a fresh one, so it's got a voltage level that's lower than the rated 9 volts. Different types of batteries have different voltages. So here we have a AA battery. So this AA battery has a voltage of 1.59 volts, and this is a 1.5 volt battery, so this is a fairly fresh one. And here's an example of a button cell that I use to light the LED. And that has a voltage of 3.25 volts. So that's a fairly fresh battery as well. That's a 3 volt battery. So this first diagram shows the basic circuit. You've got an LED with the positive lead connected to some power. So we've got the positive lead there, and we connect the LED to some power. So when measuring voltage, you don't need to break into the circuit, you're just measuring in parallel across a component. Whereas when you're measuring current, you have to break into the circuit or use a clamp meter that clamps over and uses a different way of measuring the current. So if I take our LED, a blue one in this instance, and take the positive lead, so the longer one, and put that into a breadboard. So we have the positive lead in the breadboard, all these all the way along there are all connected, and all the negative in that line are all connected. So if I take the negative lead of a multimeter and just put it into the negative and positive into there, and if we select the diode symbol, so that's just a little triangle with the little line across it, and put it to that mode, and then we select until we get the diode symbol appearing, and then we see that the LED's lit up, but we also see that there's no reading for the voltage of the LED. So one thing I've found is that for some LEDs my multimeter won't read what the forward voltage is of the diode. So what I'll try and do is if I put another multimeter across that, so just connect the minus to minus, plus to plus, and turn this on just to voltage, then we can see that this blue LED is reading a voltage of 2.5, 2.6 volts. The other thing I have is a little tester that I got off of eBay. So if I take the blue LED and if I just place it into these two pins here and just push the button, it'll go into a test mode and it'll test the LED and tell me that this one has a forward voltage of 2.75 volts. So it's a little bit different from what it was reading on the multimeter, and I'll try out a few different LEDs and see if there's an accurate way of working out the forward voltages when the meter doesn't tell you. So now I'll try it with a red LED, and we can see it's reading a forward voltage now on the diode setting, 1.92 volts. So now we'll try a yellow LED, and that's 1.95 volts. So now we'll try a green LED, that's 1.94 volts. And finally the last colour of LED I have is a white one, so that's 2.6 volts and no reading here. And that's 2.79 volts. So here we can see the figures from earlier lined from the highest voltage requirement of the LEDs down to the least. So the white and blue require more voltage to push the current through than say the red. And we see here that the values in the diode of the red meter down here and the green one here match up. And the eBay tester that we used was just a little bit out, so it was about 5% to 8% out from the values on the multimeter. So if we look at the white LED, we see it's got a forward voltage of 2.64 volts, so that means that, depending on which one's more accurate, whenever it gets to about 2.6 volts or 2.79 volts, then it should start to increase in brightness. And what I'm going to do is going to create a test circuit on a breadboard. So on a breadboard, all these 5 points here indicated by the yellow line are all joined together, and equally on the bottom side, all the 5 points indicated by the green wire are all connected, and the same for every row all the way along. On either side of the breadboard there's two rails running up and down, and all of these are connected, so all the red points are connected and all the black points. So if I connect a battery to the plus rail and the minus rail, that means I can then connect it from here up to the LED and back down again, and that'll put power through the LED. And later on we'll show you why we need to add a resistor. So in this test circuit here, we've got the power coming into the two rails here and a voltmeter that's reading the voltage across these two rails. We also have an ammeter connected up to the positive wire there, and that should show how many milliamps is flowing through. We see the LED is not lit at the moment because it's only been supplied with 1.4 volts. So from the positive rail there, through the LED, down through the negative and back there to complete the circuit. So as I turn up the voltage, as it gets closer to 2.6 volts, then the LED should start to light. So here we see the LED is glowing dimly at the moment. So here we see the LED is a bit brighter now, and it's consuming about 11 milliamps at about 3 volts. I'm not sure which one's more accurate. My bench power supply is reading that it's drawing 8 milliamps, and only 2.9 volts. You also note from the test we did earlier that the red LED had a smaller forward voltage than the white one, so there's a varying degrees of forward voltages for the different colours of LEDs, so not every LED is equal. So this would be a typical graph that would be on a data sheet, and we can see that, you know, for the white LED, when the voltage was down about 1.7 volts, then there was a low current going through the LED. As we get higher to about the 2.6, 2.7 volts, then the white LED was drawing 20 milliamps. And then we see that when you have an LED that's got a higher voltage, like 9 volts, then it's drawing more current than what the LED can sustain, and the LED just pops. So here, when this LED is set to 3.3 volts, then it's drawing about 20 milliamps of current. And then you'll see that there's a suggested current. So they suggest that you run this LED at 16 to 18 milliamps. You also see that there's a forward voltage. So you see here that they're saying for this red LED that you should run it at somewhere between 1.8 and 2.2 volts. And that matches up roughly with what we saw for the LED. It was about 1.8 to 2 volts. So what you can actually do is you can do a calculation where voltage is current times resistance, and if you think of it like a little triangle like this, where voltage is on the top and the current times resistance is on the bottom. So if you know voltage and current, you can work out what the resistance is by voltage divided by current. If you know what current, if you don't know what the current is, then it's voltage divided by resistance. And if you don't know what the voltage is, it's current times resistance. And you can do the same thing for power. So voltage in a circuit is divided up between the different components in a circuit. In a circuit, the current is the same everywhere. So if we want to have this LED drawing just to 20 milliamps, which is 0.02 amps, 1000 milliamps in an amp, then the resistor is also going to be 0.02 amps. So what we can then do is we can say, if we put a resistor in to limit the current, then the size of that resistor would need to be, because we don't know the resistance, voltage divided by current, so it's 7.22 volts for the resistor, divided by the 0.02 amps that we want, and that gives us a value that we need 361 ohms. Now there's another factor we have to consider, that this resistor is rated probably for something like 1/4 of a watt. So that means that the amount of current that we're passing through that has to be well within, or the amount of overall power putting through that has to be well within that figure. So power is voltage times current, and we also know that current is voltage divided by resistance, so we can either say power is voltage times voltage divided by resistance, or voltage squared divided by resistance, or we can substitute in that voltage is IR, so we can say I times R times the I, so power is also I squared times R. So if we take the figures here, that we have got 7.22 volts times 0.2 amps, 0.02 amps, then that gives us a figure of 0.144 watts. And if we do voltage squared divided by the number of resistance that we worked out earlier, again it comes out to the same figure, and we use this equation, again comes out to the same figure. So swapping over to the red LED, which is what these calculations was done for, then we can see that when we're approximately 2 volts on the LED, we're drawing about 17 milliamps. Resistors come in many forms. This one is a through-hole resistor that has 2 leads and resistor markings that tell you what size of resistance it is. So this one here is 10 kilo ohms. So another form of resistor are these surface mount resistors, and there's many resistors on this board. This is a variable resistor board that you can set to different amounts. So I could set this one to 10 kilo ohms for instance. And then I can move this one, so this is the 1 kilo ohms, so that would be 5 kilo ohms plus the 10 kilo ohms, giving you 15 kilo ohms. So now if I connect the variable resistor in, we've got 361 ohms. In this circuit design we have the positive lead going through a resistor to the positive lead on the LED, and then the negative lead on the LED going to the negative of the power. So what we have here is we've got the positive lead of the power coming in through the resistor, back through this orange lead to the positive lead of the LED, and then from the negative lead of the LED back through to the negative of the power. And we can see that's dropped down very dimly, and it's just drawing about 2 milliamps. So now if I put it up to the 9 volts, it should go back to roughly the same brightness as before and drawing about the same amount of current. So now we can see we're back up to about 9 volts here, drawing 20 milliamps through the LED. Now all these calculations will just be rough because this won't be the most accurate of setups. So there'll be some losses in the wires and the way the current's been measured. And what we can also do, we can increase the resistance, and what that should do is lead to a dimmer bulb that's using less current. So here we've got 1361 ohms, and it's gone from 20 milliamps down to 5 milliamps, and the bulb's got a little bit dimmer. And if we add another 1000 ohms, then it's gone down to what's that, 2 milliamps and dimmer yet. And again, if we go on to 3000, oops, then down to 1 milliamp. Oops. So as we increase the resistance and keep the voltage the same, we're dividing by a bigger number, so the current gets smaller as the resistance gets larger. One other thing you'll often find is that when you go to pick an actual resistor, you might not get one for 361 ohms, so you would just use the next resistor level up, and that would just consume slightly less current and mean that your LED just be that little bit dimmer. Cheerio.